And you're ready to go.
Okay. Good morning. My name is Chen Guangzhao. You can call me Chen. Um, I'm an MRI physicist working for Nemours Research based in Orlando. My background is MRI imaging methodology development and signal processing. So today I'm gonna briefly introduce this small project we wanna carry out at Nemours clinical site with the radiology department. So the topic is a small FOV MRI for cardiac valve imaging. The background is real-time imaging of cardiac valves is really valuable for assessing the dynamic leaflet motion. For example, in the diagnosis and characterization of valvular stenosis, regurgitation jets, and orifice geometry, etc. Right now, the state-of-art technology is echocardiography, and that's a standard way. It's a real time. We can view the images like just watching a movie at real time, but the image quality is not so favorable. Uh, on the other hand, MRI for cardiac imaging, the standard protocol is C9. Let me try to share the cursor. Yeah. Okay. Yeah. The standard protocol is C9, which requires it has a high resolution, good SNR, but it's not real time because it acquires MRI signal across multiple heartbeats, then compose the dynamic images into one heartbeat. So we have images at the different cardiac phases. Then when you view it, it looks like a movie, but it's not real time. So the proposal is to, can we achieve the real-time imaging on the MRI modality? The technology is called small FOV excitation. So we do some trade-off. We don't scan the whole imaging plan. We don't scan the whole anatomy. We just focus on a small FOV. For example, we locate the field of view on the vascular, on the cardiovascular valve and only check the motion of the valve. Okay. Next, here's still the illustration. At the left side is the current echocardiography. So you can see this real time. On the right side is the C9. For the echocardiography, we can see the leaflet here, but you can see that it's a low resolution, low SNR. It's a good thing it's a real time. And also the limitation is that we have to properly position the detector such that the sound waveform can penetrate through the physical gaps and to reach to the cardiac region and get the echo signal back. So it requires a lot of experience. So it's the position is limited. For MRI, it has a very good positioning. We can view the anatomy in whatever angle, geometry, and also it has a high resolution, good SNR. But it's not real time, just as we explained in the previous slides. So that's this. The background. We want to do that. What we want to do is the real time scanning on the MRI modality. Okay, here is a brief description of the methodology we want to use. At the left side, it's MRI system illustration. It's a big superconducting magnet. From the outside layer to the inside layer, we have superconducting magnet. It has persistent high current circulating in it with no resistance, generating a static field B0, which is normally we call 1.5 Tesla or 3 Tesla. And next to it is the gradient coil. It generates a linearly varying magnetic field such that the different body part will experience different magnetic strength, therefore different radio frequency. Then through some kind of spectral analysis, we are able to tell the location of the spins or of the pixels through their resonance frequency. Briefly, just but of course the MRI reconstruction is much more complicated than that. But in general, that's a principle behind it. And the innermost coil is the radio transmitting coil. In the standard way, we cast a RF waveform. That's a waveform something like this through the radio transmit coil. Cursor, okay, through the radio transmit coil. Therefore, human anatomy receive the energy. Then, when this energy, this energy can form an echo, which can be detected by the receiving RF coil. That's how we collect MRI signal. But anyway, the standard radio RF pulse waveform is like this. Okay, what we want to do is we create a composite RF pulse. We concatenate a sequence of multiple RF waveforms with properly calculated RF waveform shapes. Therefore, we can accept a small region as delineated here in the yellow rectangle. Therefore, we can only check the cardiovascular valve, and we see an image. In principle, we will be able to see an image like this. So this technology is called small FOV MRI or 2D RF excitation technology. That's what we want to implement on our clinical scanners. Right now, we are in contact with the vendor, Philips, to trying to reach a research agreement. Therefore, we can modify the RF pulse waveforms and deploy it on our clinical system. And then next time do some phantom scan. Then we move forward to human subject scan. In the meantime, I'm doing some simulation. Hopefully next time I can show some simulation data, and maybe even better, I can show some phantom data. Okay, considerations. Nothing comes for free. We want a real-time, high-resolution, but we have to face some challenges. First one is the RF radiation will increase because we moved from one single pulse to a composite RF pulse, which means more SAR, or specific absorption rate. So more energy deposition in human anatomy. But based on the brief calculation, is still within the limit as required by IEC, ICE, or IEC, I forgot, or FDA requirement. And also there are some hardware limitations because the RF pulse gradient waveform all need to work together in concert. Any timing discrepancy will cause some image distortion, and we have to mitigate that in the image processing reconstruction. And also the blood signal is tremendous. Therefore, we to check the valve motion, we need to eliminate the blood signal through some technologies. So that's basically the very brief introduction of this project. That's it for today. Any question?
Thanks, Chen.